Hello, hello! In this video, I will show you how to do a very simple finite element analysis with a simple part. So select new part. Let's take some time. That's fine. At least on my computer. Here we go. So you see the units of my parts are IPS. Let's use the international unit. So click right. Okay, let it start, and click right on the unit on the bottom right to select the millimeter and gram and second. Here we go. I will click on sketch and create a new sketch to start with my part. Sketch, I will use the right plane and I will pipe with two circles, 1, 2. Dimensions, I put the dimensions. This is always better to dimensions your part. Let's say 25 millimeter outside diameter, and let's say inside diameter 20. Oops, not this one. Click it twice. Here we go. Oops, I said 20, I put 25. Here we go. So this is my pipe, and I want to extrude that pipe with, let's say, 80 millimeters. So we can see what's happening there. Here we go. We have our pipe. Make sure to save. I didn't save it yet, so let's do save as, and let's save this finite element analysis. ECE215 pipe FEA. You can put your name if you want, doesn't matter, but make sure to save your part. We need, before we start the finite element analysis, we need to apply a material. So go on the materials there and click right and edit material. And let's apply the stainless steel ferrite. And you can see all the information there for the this material. Okay, we have everything in IPS. I would prefer to have them in megapascal. So click on the units and select the SE, but the SE with the megapascal. Here we go. We find the Young modulus, that is 200 gigapascal there. We have the Poisson ratio, shear modulus, the G that you know how to find, 77 gigapascal, density, tensile strength, so the maximum, the strength when it will break, and the yield strength, that the maximum strength that you want to apply to your material, maximum stress, okay, at 0.002 or whatever limits is provided, but you don't want to go over 172 megapascal at any point in the part, and apply. There, close. Okay, just long. Your part, now you should see the materials on the left, and you should see the appearance of your parts looking like materials and not anymore just the gray appearance. Now we will start the simulation. So I have the tab simulation here with a new study. If you don't have it yet, go on the gear, the little options arrow on the right, add in, and make sure that your SolidWorks simulation is checked and okay. It can take sometimes the first time you do that. I will go on simulations, new study. I want to do a static study. There's a lot of other study, but I want to do a static study. Enter. And now I have different steps. So the first one is the materials. We already have the materials. It's fine. Connections is when you have multiple parts and you want to add screws, spring, thing like that. We don't need that. We will start at fixture. So do we want to put a pin connection, fixed connections, things like that. Click right to fixture and click on fixture advisory. Okay, we will click on the right. We should have this window that open. So it's small, this one, but basically we will use the green arrow on the bottom. We want to add a fixture. We want to add, in our case, we want to add a fixed geometry. I will add it to that surface. And that's just a fix, okay? In the split. Oh, there's some other information there, but keep it fixed geometry, face, enter. And after that, we will click on create more interactions, and we want to add a load. So add a load, click down, add a load. I hope you can follow my mouse. So I want to add a load, not on the outside there, but I want to add a load on this one. So I click on this surface. I want the force to be normal. I want to be the force to be not IPS in SI, let's say 2,500 Newton. I want to pull on that surface, so reverse. And per item here, we just have one item. So the 2,500 Newton are all the way on this item. But if you have two surface and you apply this force, that will be doubled. So just be careful. And enter. Here we go. So we are done with the interactions. Make sure that it's fully constrained. If your part can move all the way over, you will not be able to make any statics analysis. So I want to be done. Continue with the next one. You say that everything looks good. We can just change the settings, but everything looks good. But let's check the change mesh size. Let's check the mesh size. So how small are the little element of finite element? So if you click on that, you can see on the left, okay, your mesh parameters, that's what is important. So the smaller one are less than 1 millimeter, the larger one 1.2 millimeters. Remember the thickness of the pipe, that's 2.5 millimeters because the outside diameter 25, inside 20, so thickness 2.5. Our elements are always smaller than the thickness, twice smaller than the thickness, so that's perfect. We have at least 2 elements per inside the part. So, okay, oops. I just click cancel because we don't change anything. And now we can click on run the study. Let me just, make it live. Run the study. It can take more or less time depending on the complexity of your part. Run. And we can see on the bottom that we have some information that pop up. We have a check deformation there. You say, oh, it looks good because your maximum deformation is 5 times 10 at the minus 6 millimeters. So it's less than 5 times 10 at minus 3 millimeters. So it's very, very small, in fact. Maybe the stainless steel is a little bit too stiff for applying just 2,500 Newton. We can click on stress to the left and show, and that will show us the different stress. And of course, even if in theory the stresses are the same everywhere, they are higher where we have the fixed connections at all the different points. But the stress that you have in the middle there, that will be the value that you will find when you do the sigma equal the force divided by the area of there. So this one is everything. I think we can find them with a probe. We need to add a probe on that. Okay, I will not do that. You can see that SolidWorks is nice. They tell you, oh, don't forget the yield strength is, remember this 172 megapascal? And we are reaching the maximum is 15.6 megapascal. So this pipe is over dimension, like times 10. So we have a safety factor of more than 10. If we divide it by the yield strengths by the Van Misses that we have right now, the maximum that we have, it's way too much. Click right on the displacement and show. That shows the displacement. The displacement is larger on that side of the pipe. Even if in theory it's spread everywhere a little bit because we are pulling on that, it's larger there. And you see the scale is times 1,000 because in fact it's very, very small. 5.6 micron, very, very small. And the strength, that would be the percentage of your displacement. If you click there, you can see it's also very small. So I did my pipe is a bit over dimensions. You can run the study definitely with something well larger. That will make more sense a little bit. So hope that helps. Let me know if you have questions. You are welcome to make different loads, to have loads in different directions, having some connections that are different, so two different surface connected, either fixed, either like with pin connections. Just make sure that it cannot move. Okay, you have enough connections to make it to stay in static. Okay, stop talking. Have fun. Bye bye.